I'd like to introduce now Jiangmin Lee, who will present his project to you.
Hello? Hello. Hello, my name is Jiangmin Lee, and this is my project, Gas-Phase Ion Chemistry and Ion Mobility of Pharmaceutical Substances in Counterfeit Formulation, Technology for Measurement and Confidence of Detection. Before I start my presentation, I would first like to acknowledge the Eisman Research Group and the Chemistry Department of NMSU. I would also like to especially thank Dr. Eisman for his aid during my project. And finally, I would like to thank my own parents. So, in my presentation, I will first go over the background information, then I'll describe about my experimental design, then I'll discuss some results, draw some conclusions, and then share some applications. So, the main problem that my project revolves around is the problem of counterfeit pharmaceuticals. Now, fake medicine is still being circulated around the world to this day, and they usually come in two different forms. One using inert compounds or like totally different other chemicals, while the other uses the same chemicals as the authentic version, however, they use it in a diluted state. So, let's say they're making like 15 pills out of one true pill. The problem with this is because since they're using the same chemicals, it's hard to detect if they're true or not. So, the type of pharmaceuticals that I focused on were anti-malarials. Now, malaria is a parasitic disease, and actually 20% of the people who die from malaria actually die because they're given fake medication. And anti-malarial pharmaceuticals also require high dosages. That's why, over time, if they're taken in a diluted state, then the medication would be rendered as obsolete. So the method that I chose to try to distinguish these medicines was the ion mobility. Now, ion mobility is dependent on the ion shape and charge. It's unique for every ion. It could be described with this formula over here, but I'll describe it with this diagram. This is the apparatus called the drift tube, and there's actually an ion source here that sends a plume of ions into the drift tube, which is stopped by the shutter. The shutter turns on and off. When the shutter does turn on, all these ions race towards the detector. Of course, some of the ions would travel faster than the others, and the drift time down here is the time between the ions being released and the ions being detected over here. The intensity, which is shown by the y-axis here, is the amount of these ions hitting the detector at that time. Now, here's a short clip. Okay, and here's a short clip of my experiment. This over here is a laser that's actually hitting a tablet. Over here is an electrospray which sprays the ion plume into the drift tube, which is this apparatus back here. So, here's an overview of the rest of my experiment. Again, there's electrospray down here, there's the sample, and then the laser hitting the sample. The laser is actually vaporizing the surface of the sample, so the ion plume that's sent by the syringe picks them up and carries it into the drift tube, and it passes the shutter and hits the detector. Actually, back here there's a gas flow that's flowing in the opposite direction, and this is because this is to ensure that these ions aren't sticking to the drift rings on the sides, and to create an environment inside the drift tube itself. Once it's being detected, then the signal is amplified and then marked onto a computer. So, here's the graph of atovaquone. Atovaquone is one of the active ingredients for Malarum, which is an anti-malarial pharmaceutical. And over here, atovaquone, you can see, has a drift time of 21.38 milliseconds. I did the same with another chemical, plaquenil, which is another anti-malarial pharmaceutical, and its active ingredient is the hydroxychloroquine. And its own drift time can be seen at 20.08 milliseconds. Now, with these numbers, I generated this table where there's the reduced mobilities. And the 2,6-diterbutylpyridine is actually a standard chemical that's used in many IMS studies. And using this number, I was able to compare it with these other chemicals and actually generate reduced mobility numbers for the other active ingredients that existed in my experiment. Now, if anyone else wanted to do an experiment with these chemicals in the IMS, they could actually use these numbers as a reference, because since every drift tube is different, then they could use these to calibrate, because these numbers are relative to the chemical itself, not to the drift tube or the experiment. So here's an actual signal from the Malarum tablet itself. This is the ELDI, the one shown with the laser previously. And since I found that atovaquone was at 21.38 milliseconds, after these many spikes, I was able to distinguish that this peak was actually the peak for atovaquone. Later on, I also got to discover that this was proguanil, which is the second active ingredient for Malarum. I actually moved on to another method, the ESI-IMS, where it's just called the electrospray ionization. And this takes out the laser, but instead I had to crush the tablets and then put them into the solvent that the syringe was spraying. And then, now even though there's no laser, I was able to ionize these by the high voltage from the electrospray and just directly spray it into the drift tube. Now you can see that the graph over here now has much more distinguished peaks. And this is what I actually used for the different concentrations as I changed the concentrations of the vials to simulate basically fake medicine by diluting it. So my quantitative response, you can see that both response curves for the hydroxychloroquine and the atovaquone do exhibit a positive correlation between the concentration and the intensity. The atovaquone does have a smaller graph than the hydroxychloroquine, but this could be attributed to the fact that hydroxychloroquine does have a higher proton affinity, thus be more affected by the electric fields in the drift tube. However, both of these still exhibited that positive correlation, so I was able to conclude that the ESI does work. So in conclusion, I was able to find the reduced mobility numbers for actually multiple antimalarial chemicals. Additionally, I was also able to say that the ESI-IMS is a plausible way to distinguish between the fake or the true medicine, because it has a relationship between the concentration and the intensity that's being shown. Some additional applications include, apart from like that's from medicine, but also include trying to find the concentration of other ingredients in other products, such as caffeine. This could also be used in security, where the liquid could be tested to see if there's too high of a concentration of a volatile liquid. So, well, that's my presentation. Thank you.